with Yilei Chen, who's going to tell us about cryptanalysis of candidate program obfuscators. Thanks, Yilei.
Thanks, Shweta. Thanks, organizer, and thanks all the participants and all of you who are watching us on YouTube. That you attend this talk in such a difficult time in our life, and in some sense, like this whole program also reminds us of rethinking the meaning of our life, what we are doing, how can we do to contribute to the human being societies to overcome this crisis. I guess so. Part of what we can contribute is to build up a sense of science, and also like I guess for this talk, one of the immediate implication will be hold all of you in the shelter, so you will not go outside, and hopefully this will bring a little bit of joy to your life, and also more open problems to be solved after this talk. So let me get started. The topic of today is going to be cryptanalysis of candidate branching program obfuscators. And at the same time, I would also like to remind that if you hear a big noise like a don, 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 it's not likely to be an earthquake. We have a neighbor, they have 2 kids, and they are frequently practicing for Olympics. So, you know, I think this, like the switch of all the program into online, it also gives a big opportunity to all the participants. Like, so if you get lost during the talk, right, so you can just turn off your screen and do jumping jacks in the background, and no one will heard about it. And you can come back if you find something interesting. And also, you know, like right now, everyone is in the home, and you know, you're watching other people also working in the garden, and you're also thinking about like a travel back to time. And I would like to start this talk also in the beginning of this new century, right? You know, in the beginning of year 2000, everything exciting. Also, it's very exciting for the field of program obfuscation, because finally there's formal attempts to define program obfuscation. The first attempts of Hada and Barak et al., they tried something that is later to show to be impossible. But there's one definition which is left until now, say indistinguishability obfuscation. Say if 2 programs are functionally equivalent, so maybe you can obfuscate them so they are computationally indistinguishable. It turns out this definition survives, and 13 years later, we even have a candidate. Papers of candidate multilinear maps, and also candidate indistinguishability obfuscator for all circuits from basically candidate multilinear maps. So, you know, this brings the whole excitement to the field. And also at that stage, so they are called a candidate because at the moment they are proposed, we don't know how to base the security of them based on the problem we have studied. Like we have some ideas that they can be hard based on our previous understanding of problems on ideal lattices, but we don't know how to do the reduction. We don't know how to like analyze them. But assuming this multilinear map candidates and IO candidates are secure, this opens like the whole imagination. I would say they start the age of discovering the crypto land again. So really what happened after 2013, and in a short period of like 3 to 4 years, we have seen that if you assume this multilinear maps and the program obfuscation are secure, or more or less IO is secure, then you can show all the crypto applications that we don't know how to achieve before. So this is only a partial list. And at that time, we sort of think about IO as the central hub of cryptography, as this picture indicates. And at that moment, we are also thinking like, so after you show so many great applications, are the multilinear maps and the program obfuscator and underlying this application, are they secure? Like it's the time to take the very serious look at the security. So I would like to explain this via two connections. So first is the multilinear map to obfuscation. In the beginning, the first work of Gaga et al. Is showing a candidate. Okay, so there are some security analysis, more work has to be done. So later, I think two important work which shows if the multilinear maps, it achieves ideal security. In short term, what does ideal security mean? It's sort of like you can assume the multilinear maps, they are working as good as what we understand on the bilinear map from Paris. So they are kind of ideal. There's not many corner cases. So if the multilinear map achieves that security, then we can achieve VBB obfuscation. Like it's almost like a same IO you can build from that. So also you can weaker the underlying assumption to a concrete assumption called multilinear subgroup elimination assumption. So from that you can also build IO. So basically the moral is if the multilinear map is good enough, then IO exists. So at that time, the connection from multilinear map from lattices is still a big problem. I think right now it's still a big problem. So after the work of Gaga et al., there are three more candidates. They are all more or less based on lattice-ish problems. Actually, they are all modified from the previous FHE scheme that you can see the kind of like the like this is approximate GCD, and this is a more GSW modified. But we don't know how to base the security on a concrete lattice problem at that time. And in fact, in 2015, we already see attack, the check of Zhonghan, Li Yu, and Steli. They actually break the CERT13 multilinear maps in some setting. So it already shows a warning sign. And let's go back to 2015. So usually when we talk about the security of multilinear maps, we think about two benchmarks. So one is to do a multi-party non-interactive key agreement from multilinear maps. And the other benchmark is IO. So we can think about making a list of the status in this table. Like here is the multilinear maps, and here is the two benchmark applications. So in 2015, we have already seen the CRT13, at least some simple case is broken in both of these two benchmarks. And a year later, actually, most of the key exchange are broken, and the IO candidates, there's a partial attack on IO based on GGH13, and GGH15 is still standing at that moment. And so if you combine this with the previous picture, the attack on IO, it really puts a threat on all the application we have shown in the previous 3 years. So, there's more warning sign on what is going on. And at that time, in 2016, I was in the middle of my PhD. And you're thinking, so this is the picture you see in the crypto land. And you're thinking about yourself, what can you do? What can you do to contribute to crypto? And also in general, like we are facing different choices every day in your life. So I would also like to let the audience, flashback. So what are the choices you made in your life, 4 years ago? So, people have to make choices every day in their life, and even for the characters in the movie. So let's look back into a movie in 1962. So the school kids are asked by their professors to write essays to describe their favorite animals. So one little girl of 8 chose a bird, and let's see what she says. A bird is an animal with an inside and an outside. If you remove the outside, you see the inside. If you remove the inside, and you see the soul. And this is my choice at that time. I want to see the soul of obfuscation. And I think this is the choice of actually many of the participants in the audience, and the outcomes comes in different ways. Today, I would like to take you through a tour to see the soul of obfuscation. And I will continue for a few more minutes as the overview of all the obfuscators and the attacks and overview of them. And I will talk specifically about two attacks that I have worked on obfuscator based on GGH15. I will later explain why do we focus on this candidate. And in some sense, explaining the technical details of obfuscation are kind of difficult within 1 hour, but I hope I can give you a brief idea. And I would like to also mention two interesting open problems. Each of them occur in one of the attack. So it turns out these attacks are, these open problems are extremely simple to describe, even without going through the obfuscators. But since they are motivated from them, I will still go through the attacks and then mention. So here's a problem. If you can solve, it will make the attack better. So hopefully we will have enough time to discuss these two open problems. So in the rest of the overview, I would like to talk about three things. So really like the previous are also overview. So let me conclude the overview by addressing three questions. So how are the other IO candidates doing right now? Since we are going to talk about one of them, I would like to wrap up with the others. And also, I would like to talk about what are the general attack strategies we use in the last 7 years of breaking IOs and multilinear maps. And finally, I would like to also tell you why do we focus on GGH15. So first, how are the other IO candidates doing? So as you can see from this picture, previously we all know all the crypto from IO. Right? And so you can see something is turning into green in this picture because so after all the attack shows up, so we need all these applications to come back to help IO. And so this is really like the picture backwards. So right now we are trying all the methods in building IO. And you can see this functional encryption becomes a very big component because right now you can also show succinct functional encryption implies back IO. And right now, actually, this branch is a very fruitful branch. There's a lot of attempts actually to build a succinct functional encryption in order to show IO. So that turns out to be showing more chance of getting more modular analysis. So although I think all of them are not well understood at this moment, we are still exploring. So also besides functional encryption multilinear maps, we also see a lot of new attempts in recent year, where there's also even attempts like before 2013, there's a proposal by Ron and Vinod of using black box pseudo-free groups, although we don't know how to do that either, and all other attempts. So we are still in the like the long sentence short. We are still in the exploration stage, So this is the big picture.
Yilei. Hi, I have a question. So here you say that asterisk means not published, right?
Yeah.
And you have algebraic geometry asterisk.
Yeah. So that means the three linear map, there's a candidate. We are still trying to understand what's going on. Right?
Oh, that's cool.
So that's like 2 years ago, there's a candidate, then the first version is broken, then there's another version which is longer. So we are trying to understand.
I mean, is this on ePrint?
So this is on archive. I can send you the link afterwards.
Okay, great, thanks.
All right. Also, Okay, so let me also talk about the general strategies of breaking I/O. So you see, there's a lot of ways to get I/O from the previous picture, but the general ways of breaking I/O are there are actually some common points. So obviously, to break I/O, you need to find two programs that are functionally equivalent and distinguish the obfuscated version of them afterwards. So you need to do that obvious step. So some other common strategies you use to break I/O is, so we see very frequently that the attack strategy goes as follows. So we are trying to find equations or relations of the unknown variables over the integers or rationals instead of over the finite field. So in more general term, we are trying to move from a characteristic Q field to like a characteristic zero or the base ring. So the basic intuition is the problems are usually easier to solve over integers or rationals. We have more tools over there. The other obvious strategy is we need to turn high degree equations into linear equations. And looking ahead, like in all the recent IO candidates and their cryptanalysis attempts, we seems to have many ways to prevent number two, meaning that we seems to have a lot of intuitions that so some equations we can put them into high degree that it's very difficult to linearize. But one seems to be hard to prevent right now for all the noisy-based IO candidates because they are still based on like the, and many of them are still based on the correctness check by saying if an element is big or small over FQ, and therefore you can still find the relations over the integers and the Q. If you watch the talk of Amit and others yesterday, you can also realize. So right now, in the case that when it's hard to remove, we are actually trying to find hard problems, which is even hard over the integers and the rationals, so that because this is hard to prevent if you use a noisy linear. Shall I answer questions? I see like.
No, I think you need not stop
Okay.
for that.
Okay.
Yeah.
So if you see interesting question, remind me.
Yeah, certainly.
Yeah. Okay. So also, in addition to the common attacking strategy, there's also interesting attack motivated by breaking IO or multilinear maps. That these are interesting attack on specific components of obfuscation. So I know two big categories. So one of them is a lot of lattice attack that they can break variants of N-true that are motivated by multilinear maps or FHE. And the other big category is all the sum of square attack on like low degree PRGs. You know, so I think so these are very interesting attacks that is motivated by brick IO, but also they have wider impact in terms of it adds to our toolkit of cryptanalysis. So finally, why do we focus on GGH15 today? Well, one of the reasons is, I think, because we know, right now we also know a lot of safe modes of using the GGH15 multilinear maps to do a lot of stuff besides IO. So we still don't know how to achieve IO from a safe mode of GGH15 based on lattices. But we can use a safe mode which is as secure as LWE to achieve private constraint PRF and the lockable obfuscation and trader tracing also from direct construction. So this is a commercial. So you can also see some of my talks on YouTube about the safe mode. I'm not going to talk about today. And upcoming today in the other two Simon seminars about lockable obfuscation and the trader tracing. So I would recommend you to stick into this channel. So this is the end of my overview. And starting now, let me take you through the soul of obfuscation, and the obfuscation in the sense of which is based on the the Gaga et al. Obfuscator combined with GG15 multilinear maps. So really the movie of saying if you remove the outside, you see the inside, and you see the inside, remove the inside, you see the soul is very accurate for obfuscators, because the candidate obfuscator from Gaga et al., it also, in my point of view, it has like 4 layers. And if you unwrap layer by layer, we will see what's going on. So for the candidate IO of Gaga et al., I see it is building from like 3 steps. So first, we need to find the right representation of the plaintext program. So if you have a C code, Python code, you need to convert it into a certain format of plaintext. So then I think of we add 3 safeguards. So the safeguards, we are sort of thinking about them as to be used to randomize the plaintext program. And the purpose is to prevent illegal operations. In the end, after you wrap it up with 3 safeguards, we wrap all of them together with multilinear maps, one of your favorite multilinear maps. So we think about multilinear map as the source of computational hardness. So although precisely speaking, multilinear maps is not the only computational hardness. But in this talk, let's think in this way. So multilinear maps, we in the group representation, we think about we encode all the element we want to multiply into the exponent, and the multilinear maps gives you a way to compute the product of them in the exponent without revealing them in the clear. So let me start describing now, layer by layer. So the first layer, which is actually the most important layer, is we need to fix a representation of the plaintext program. So to fix the representation of a plaintext program, we use Barrington theorem. Say, suppose the program we begin with can be the depth Boolean circuit. So according to Barrington theorem, we can convert all the log depth Boolean circuits into matrix branching program. So let me do, this is one of my favorite paper from Stock and Fox, because literally the proof is only 1 line. So here's, let me give you a pictorial proof of how to represent an AND gate. So suppose you want to represent an AND gate by a program which do subset product computation. So here's the way you do it. So suppose we want to do AND gate, meaning like only if the 2 input wires goes to 1, you output 1, and the other case, you output 0. So let's use the identity matrix to represent 0, and the non-identity matrix to represent non-zero. And so here's the way you represent all the programs. So you say in 1, you choose a lot of non-identity matrices where P and P inverse corresponding to the first wire, and the Q and the Q inverse correspond to the second wire. So to evaluate, you do the subset sum according to the input choice. So for example, if the input is 1, 1, you do P times Q times P inverse times Q inverse, and this gives a non-identity matrix. So you can see all the other choices gives identity matrix. Like if you get 1, 0, it will get P times I times P inverse times I, you get identity matrix. So to bootstrap AND into log depth circuits, so you also need OR, and really it's a recursive composition. So you can convert a log depth Boolean circuit into a polynomially long branching program. I would like you to remember this picture, because this is actually the key of the attack. Let's move on. So after you convert everything into a branching program, for the purpose of putting it into multilinear map in the end, we think about, we have a functional branch where we have all the identity matrix and non-identity matrix. You can do subset products. In the end, you compare whether the product is equal to I or not. So for the purpose of adding all the safeguards, they also create a dummy branch where all the B prime are actually identity. So whatever you multiply is still identity. And in the end, you will subtract them and compare. We will see in a moment why do we have a dummy branch. This is for the purpose of adding safeguards. So now let's start adding safeguards. So the first step is Killian randomization. You try to glue things together. You randomize each matrices. They will cancel out in the end. So the second step, which will be the key to the one of the attack I described, is they add bundling scalars to prevent mixed input attack. So what is a mixed input attack? So if you see the branching program representation, like the first bit of the input can choose 2 steps in this picture. So what if you choose inconsistent input between these 2 steps? So you can actually learn more information about the program by just doing illegal computations. So adding bundling scalars with all the cancel relation set up between the functional branch and the dummy branch, you can prevent the adversary from learning illegal information from doing illegal computations.
So, Yilei, I have a quick question.
Yes, please.
How do these 2 branches interact with each other?
So this is can be described without all the safeguards. So in the end, the goal is to say, in the end, after you wrap everything up with multilinear maps, you compute it by the following. You do the subset product in the functional branch, and you do the subset product in the dummy branch. And in the case where the output is 0, meaning that the functional branch goes to identity, then you subtract the functional branch and the dummy branch, you will get 0. So the 0 test of the multilinear maps will tell you 0. If not, then you will get random.
So
Okay.
you're saying that they just run in parallel. So you just do the computation on the main branch separately and the dummy branch separately, and you just subtract them in the end.
Right. Okay, so let me continue by describing the other safeguard. So the last safeguard is another layer. So we also pad some diagonal entries on the branching program, and we add bookends to cancel them out. So let's zoom in. So here is the original branching program, like permutation matrices. So we add 2 entries in the diagonal. They are random. They're just to make the program more random. And in the end, we have a way to cancel them out by putting a row vector in the beginning where this is 0, and put a column vector in the end where this part is 0. So you can see after computing everything together, this random diagonal entries goes away. And in the end, after putting all the safeguards, you wrap all of the program by multilinear maps. I haven't described the multilinear map construction, but more or less you can put one of them on our side. So maybe some of you has already lost because if this is the first time you see an obfuscator, you probably already get lost, and you're probably doing jumping jacks in the background. So let me just give you a quick highlight. So if you get lost, don't worry. You only need to remember 2 parts. The first part is remember the representation of the plaintext program. We use permutation branching programs. And also the safeguard 2, we use bundling scalars. So this will be the key for the attack, one of the attack I describe in a minute. So let me continue by also give you a recap of GGH15 multilinear maps. So by now, I guess everyone knows LWE. What is LWE? You have a public matrix and also an LW sample, which is S times A plus a little bit noise. So the search LW problem says, if I give you A and Y, it's difficult to find S. The decisional LW problem says it's hard to distinguish A and Y from random. So in this talk, I would like you to use this graphic notation. So usually with this background, I mean the matrix is random. With this background, like the white color background, it means it's a small element or in FQ. And everything else which is unclear at this moment will be put into the unclear color. So what is the view of GGH15? So we think about the multilinear maps in the group representation as follows. So all the secrets are in the exponent of a group where the discrete log problem is potentially hard. And GGH15 provides a ring LW analogy of this view. So say, instead of putting all the secrets in the exponent of a group, I put all the secrets in the secret place in the LW samples and hope there's a way to publicly compute them into the secret, into a product of the secret in the final LW sample. So the whole point is how to find a way to map them without revealing the secrets in the middle. So let me explain GGH15 for one multiplication in 2 steps. So think about we are just trying to encode the secret S1 and S2 so that we can multiply them without revealing what they are. So in step 1, we create LW samples with respect to the public matrix of each of them. So, if you output them, it will be no problem. So in the second step, we are trying to connect these 2 samples by building a bridge between them. So I'll use the trapdoor of I-1 to sample a small matrix such that A minus Y times DI equals to Y. And in this talk, we will think about D2 as the encoding of S2, D1 as the encoding of S1. So let me first take you through the functionality of this simple example. So record goal is to kind of like multiply them secretly and achieve the product in the final LW sample. And so right now, just imagine the D1 and the D2 does not reveal S1 and S2. This is the secret goal. But let's go through the functionality first. Let's just open them. So we say A0 times D1 equals to the first LW sample, and you can write them separately, multiplying D2. And let's do again over A1 times D2. So A1 times D2 equals to Y2, and it opens up to S2 times A2 and E2. And then finally, you can see that these parts is like a small times small plus small times small. It's still relatively small. And the first part is look like the product in the LW secret. So this is the view of the functionality of GGH15. Very frequently in the literature, so including the obfuscation candidate and all the other safe stuff we built from GGH15, we use this subset product encoding. So we're thinking of the goal as encoding all the secrets, putting into the way that later we are going to compute subset product over the secret times A plus more noise. And the encoding of all of them will look like a leading term A0, and you times like a matrix with bigger dimension D, or the D, choosing subset products. So we think about D as the encoding of S, and in the end, you will choose how to multiply by the input index. The input is a bit string that choose which to multiply. So in the context of GGH15 plus the GGH-RSW obfuscator, this connection can be viewed in the following way. So we think about all the previous Bertrand program we have wrapped up with safeguards 1, 2, 3 as the big secret term. So this big secret term is it's not a big in the sense that they are big in the FQ, but it's a complicated secret term. So you put this secret term into the corresponding position of the secret term of the LW samples, and use GGH15 to build a chain of each input steps has 2 choices, and you put all the secrets into the secrets of the GGH15 chain. So really, the obfuscation plus GGH15, all the program you will see is the following. You will see A0 and a bunch of matrices as the functional branch. So these will encode the branching program wrapped by all the safeguards in the LW secret. And you will also see the dummy branch, like there's also all the encodings in the dummy branch. So you will see all the matrices on this picture except AL. AL, you don't have to see it. I just want to point out, in the end, you need to have a common AL to achieve the functionality. All right. So after describing, the construction, you ask, thank you very much. So where is the soul of this obfuscator? Well, in some sense, the soul of the obfuscator has already been described. Basically, to understand what's going on, I think half of the work you have to do is to first understand the construction and write it in the notations that you're familiar with, and explain your own way in some sense. But you will still ask, like, what's the really the key point in the attack? So the key point in the attack, we need to use the weakness in GGH15, and together with kind of some vulnerabilities you will exploit in the previous 3 safeguards and the plaintext. In this talk, the weakness will be in the bundling scalars and all the plaintext branching program. For different candidates, the weak points may be different. So right now, let me tell you the key idea behind the attack to the multilinear map. So this is going to be, I think, probably the most important few slides from now. In fact, the key idea of the attack to GGH15, it already shows up in the work of Coron et al. To break the GGH15 based key exchange. So now look at your screen carefully. So if you do the honest evaluation of just the 2 steps, so this is the encoding I described to you before. So you will see a big component plus small components. So the small components are not a small random, they have structures. So from now, let's assume S1 times S2 equals to 0. So we say there's a lot of evaluations in the program obfuscation context, which goes to all 0. And all what you left is the small component. You can see A times the encoding times encoding equals to the sum of 2 products, which actually holds over integer. By holding the evaluation mod q, but the result you get can be expressed into the sum of 2 products over the integers if you set up the variables over integers. So why is this observation useful? Let's continue. We need more space to see how to rearrange this small component. So we rearrange in the way that we put all the secrets and error corresponding to the first encoding in the concatenation of the first matrix as a kind of a row matrix, and the error and the encoding for the second encoding into a column matrix, into this shape. So you can rewrite just to reorganize all the components. So right now the left becomes come from one encoding, the right comes from all the information from the other encoding. So still, how do we continue with the attack? So right now, let's generalize slightly. So we think about we can get a lot of evaluation in the following form. So it's really A times dx, where there's a lot of choices in the x part, and there's a lot of choices in the z part. And you can do a combinatoric organization of a lot of evaluations. So let me be more concrete. So if we have more inputs at the X zone and the Z zone, so we can get more evaluations on WX1, Z1, WX1, Z2. You can combine them into think about there's n choices in X zone, n choices in Z zone. There's n times n many different combinations. And you put all the evaluation result and form them into a matrix. Then you can express the matrix into the product of two matrices, and this relation all holds over integers. So how do we use this fact? To use this fact that we can decompose into the product, we need to understand what is the important information we want to extract from these candidates. So really, the matrix on the right-hand side, it's all errors, and the encodings are from Gaussian distribution. So right now we say they are sort of random and small. What really we want to extract is the information from the secret term on the left. So this is still random, but we want to extract some information from the secret terms. So from now, let's assume we can write the big matrix as W. So W is you can compute from honest evaluation, and you can write it into X times Z. And Z is useless. X contains useful information. And so here is a big picture of the two attacks to the concrete obfuscation candidates. So in CGH17, what we do is we collect a matrix W such that X is kind of a tall matrix and Z is a square matrix. And by computing the left kernel of W, you're actually extracting information about the left kernel of X, and this part contains information about the secrets. In the later attack, we actually do something much simpler. We just compute the rank of W, and we show this already reveals information about the branching program directly. So in the rest of the talk, let me briefly go over these two attacks into details, and also explain to you the open problems. So the first let's pick two programs which are functionally equivalent and as the target of the attack. So we think about the following two programs. So the first program have all the identity matrix. You'll get all 0 outputs in the end. The second program has two non-identity matrix planned in two positions controlled by the first input. But you can see they will cancel out in all the evaluations, so they are functionally equivalent. Our goal is to extract the boundary scalars in the X zone. So for example, the boundary scalars here and here. So then you can use the boundary scalars to conduct the mixed input attack. So first, let me explain how to get the evaluations over 0. So what you do is you partition the evaluation, the input indices into the X part and the Z part. And for now, let's assume they can be chosen independently. So you get a bunch of evaluation on, for example, 0, 0, 0, 0, 0, 0. You change the first bit a little bit. Then you change the second part correspondingly. You collect a lot of evaluation. Yes.
Sorry, there's a question. You can read it on your screen. Yeah.
The attack depends on the fact that the relation on the noise is low degree. Yeah. There are ways of making this high degree that may avoid an attack. So that's a good question. So right now we are using...
Maybe we can repeat the question for the benefit of the recording.
Okay, yes. So in the previous slide, I think maybe the best place to start with is here. I think everyone can see the screen. So we think about, all the evaluations is decomposing to the product. So basically it's a degree 2 relation. And in this simple example, you can achieve, you can decompose into linear relations. But actually, even for this, just for the GGHISW candidate, if you think about all the indices are repeating like 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, in that extreme case, it is already very difficult to decompose into this product. So in some sense, like I will show in the end, there will be one setting of even the first candidate that in one setting, we cannot find a low degree decomposition of small relations. So the short answer is there are ways, and it's already there. It's kind of the feeling that we don't know how to find ways to narrow down the degree. It's not clear, it's impossible. Hope this gives a brief summary of this. This is a great question. This happens in all the attack of all the other candidates in general. So let me continue with in the setting that we can decompose.
So Yilei, sorry, 1 second. So to follow up on Rachel's question, you're saying that this attack can be overcome if you sort of repeat the branching, if you sort of concatenate the branching program with itself security parameter number of times.
Right.
That's what you're saying, but we don't know how to prove anything about it.
Correct.
So it gives you a candidate. It gives you a candidate IO which resists these attacks.
Right. In fact, I would motivate even an open problem of how to attack it, even if you repeat many times. Yeah, we will see. So since we mentioned this, let me just remind you again. In the first example of a program to attack, we actually assume, there's an X zone where all the indices are 1, 2, 1, 2, and the Z zone where there are all the indices which are not from 1 to 1, 2. In the sense we are using the input partitioning feature. What I was describing before is if you don't have this input partitioning feature, then we need to run a more complex attack. And at some point, the current technique doesn't work. Okay. So let's resume. So in the case that you can partition the input into 2 parts, so you can organize this matrix in the following way by just evaluating on all the inputs. So right now, if you rewrite this equation into the equation we previously described, like there's a big component X, there's a big component Z, there's useful information in X. What we can do is look at W, compute its left kernel, and you're guaranteed that Z is a 4 rank with high probability, it's square. So the left kernel of W is really the left kernel of X. Excuse me. So after looking at, you computed the left kernel of X, let's see what you can extract. Excuse me. So if you see the left kernel of X, so what you really see is you will see a bunch of linear system of equations over the bundling scalars. And we are trying to use the homogeneous feature of these equations to get possibly the ratio of these scalars. This is what you will get in the 3rd step of the attack. So here we are almost close to the first interesting open problem. So recall that the goal of the mixed input attacks is to learn the scalars, and then you can do the mixed input attack. So something I haven't told you before is if you put the GGHISW and the GGH15 in the original setting of GGH15, they say, let's use the ring setting. So what you can get is all the ratios over the like the fractional ideal of where all the coefficients might be big. So what we really want is to get the small multiples of each of them. So at this moment, this seems like an easy problem. I would like to remind you, this looks like the entry problem, except that we don't have mod Q. So we know entry problem is hard if you have all of this stuff a mod Q, then getting the small multiples of each of them is difficult. But right now we don't have mod Q. They are still big. Seems to be an easy problem. It turns out this problem we also don't know how to solve at that time. So at that time we only know, for certain parameters, because you have multiple samples, you can use averaging attack. But in general, you get a ratio over the fractional ideal. You still need quantum polynomial time algorithm or classical sub-exponential time algorithm to find the small multiples of each of them. So this motivates the first interesting problem I want to tell you, that it's called entry problem without mod Q. So let's say you are given just a one sample, like H equals to F over G, over the rational ring. And sorry, not so it's it can be expressed as a rational polynomial in a ring. So where F and G are sampled with small coefficients, like what normal entry do. The only difference is you have H without mod Q, so you get somehow even more information. And the task is to find small multiples of F and G. So this problem, it turns out not to be easy. Still, even today it's 2020. I don't know how to solve them without using quantum. Yeah, so this is the first interesting problem I want to leave. I would like to mention that the problem I leave might be very simple compared to the problems you see yesterday. But it turns out even for this interesting problem, we don't know how to solve. And if this problem turns out to be hard, it actually gives you a candidate where a problem looks like lattices, and it's defined over the integer or rational, but we don't know how to at least break the one-wayness. Okay, so.
Yilei, sorry. So I'm
Yeah.
trying to understand why this problem is hard without the mod Q. You can write this F over G as a product of two small matrices, right? The matrix that computes the multiplication by G inverse. The G inverse is actually has small coefficients over the rationals, right? The inverse of a small matrix has small entries as well over the over the rationals, and now you can write it as sort of a G inverse times F, or rather the matrix that computes G inverse times this vector of coefficients of F, and you're asking to sort of like do this decomposition over the. So yeah. Okay, I see. So you're saying we don't know how to solve this problem.
Yeah.
Okay. All right. Okay.
Yeah, so
okay, thanks.
Let's continue. So really a quick summarize of the CGH 17 attack is, so you run through a bunch of steps, they are linear algebra, but in the end you meet a step which requires quantum and sub-exponential. So really the status of CGH 17, it's a quantum attack because of the last step. So I would say there are two limitations of the first attack. So first, you need a quantum polynomial or sub-exponential classical in the last step. And the attack only applies to branching programs where the indices can be partitioned into X zone and Z zone. Like first part is 1, 2, 1, 2. The second part is 3, 4, 3, 4. So we can overcome some of them in the second attack, and the attack actually has a much simpler algorithm. It's called a rank attack. So after you get in the matrix W, so instead of computing the left kernel of W, extracting the scalars, make them smaller, and then we do the mixed input attack, what we can do is let's just directly compute the rank of W. So let's see what the rank of W might tell you, and I will later explain what we do. So as I mentioned before, you can organize the matrix so that the Z zone is high rank with high probability. So the X zone has one error component, which is also full rank with high probability. But the rank of this S component may leak information about. And this is the fact we're gonna make use of. So let's try to find two programs where this attack can apply. So first, let's cheat a little bit. So let's find two functional inequivalent programs that it's easy to describe what's the rank difference. If you calculate the rank of W carefully, you will see in the first case, the rank of W depends on a submatrix like this. In the second program, the rank of W depends on a submatrix like this. So this is like a rank N, this is a rank 2N. So now let's find a real example. In the real example, we think about like all the inputs are partitioned into two zones, and now they can like interleave with each other. So it can be 1 2 1 2 3 4 3 4 1 2 1 2 3 4 3 4, and in the 1 2 1 2 place, there will be P and P inverse canceling out each other on some input bits. So it turns out for this type of branching program, the attack is the same, except is you organize a matrix W, which is with much bigger dimension. The algorithm is the same. You just evaluate, organize as a matrix. The only difference is the analysis is going to be much more complex. So in analysis, we crucially use a matrix product switching trick, introducing the work of Apon et al. And Kohn et al. They're actually using this trick to extend attack on CRT13 and the GG13 multilinear maps. Roughly speaking, it says if you have a matrix product of 4 matrices, you can rewrite them into the way that the A and C can be all put into a vector in the left, and B and D can be all put in a vector in the right. It's just that the dimension blows up. And in the end, in the rank attack, you will see the program 1 case look like this, the program 2 case look like this. It's just the M is a bigger matrix, depends on P, which is very complex, but you can see the rank difference. And in general, you can use this index switching attack to switch back the indices which are interleaving to something which is partitioning. And in general, if the index repeat for C times, the dimension of the matrix you accumulate has to be 2 to the 2 times C. So really, if you repeat for constant times, you can still attack. If you repeat for security parameter many times, then the matrix you collect in the attack is also exponential dimension. I want to end this talk by a quick remark that you can also use this attack to break all the PRF from matrix products. I think I'm short in time. Let me tell you the result. If you have a matrix product PRF from all the interleaving products, so then actually you can break them in time 2 to the C, where C is the time of repetition of the indices. In this work, we also provide a simpler proof of the matrix switching lemma. At this moment, I would like to remind another interesting problem that, so this problem I have started thinking for less number of period of time. It's only started recently. So can we show a better attack for matrix PRF or IO using quantum algorithm? So briefly on the background, so we also know some quantum advantage in solving linear algebra problem. So if the matrix satisfies some tricky conditions, then you can solve linear algebra of a matrix with actually exponential dimension in polynomial time. So although this depends on how do you represent the matrix, and also how do you represent the input-output vectors. You can also modify the algorithm in different ways to come up with an algorithm that decides whether the rank of input matrix is super high or super low, again, the running time depends on a lot of conditions in the matrix, like all the singular values, etc. So what is this algorithm useful for? So if you can show that some kind of the quantum algorithm which decides the rank of a matrix is widely applied, then you might be able to apply it on all the matrix branching programs that represents a PRF obtained from Barrington theorem. In fact, we have such a candidate, not a candidate in some sense, in the work of Mark. He has already proved that the NC1 PRF from Lattices is secure in the quantum query model. So it's really interesting to understand the connection between the possible quantum algorithm of deciding the rank and the security of this PRF computable in NC1 and presumably quantum secure. So I'd like to wrap up my talk. So this is the status of all the IO candidates under the framework of Garg et al. So still, under the current understanding, if you repeat the branching program for superpolynomial, security parameter many times, or you use the dual input branching program, we don't know any attacks on all of these settings. In fact, we don't know a quantum attack specifically for GGH15. And in the work of CVW18, we provide another variant of the obfuscation candidate where there are two differences. So first, we emphasize on the oblivious branching program has to repeat the indices for n times, and we make the bundling factors as non-commutative. It turns out you can do so. So this is attacked using statistical attack by Chen et al., but we can fix it by changing the parameters. And I would like to conclude this talk by rephrase the two open problems. Maybe they can solve within a day. The first problem is entry problem without multi-Q. The other is think about better rank attack using quantum algorithms. This is the end of the talk. I can take questions.
So we're out of time. Maybe we can just take one quick question.
Yeah.
So I have a quick question.
Yeah.
Yilei, just on the open problem slide. So just one slide before. So H is already a small multiple of F. You wanted something even smaller than that?
So it turns out it depends on how do you represent H over QX over phi x. Mm-hmm. So let me give you a high-level picture of what's the possible representation of H. So think about you get an H in the following form. All the coefficients are in rational. So you can represent it in a very stupid way that all the denominators are the big common denominators. So it can be as large as the norm of G. Mm-hmm. So if you are giving H in that way, and this is what you actually obtain in the experiment, it's actually not clear how to find a small representative in both the denominator and the denominator. Mm-hmm. The numerator. So it depends on the representation you get for H. The most convenient way is to think about that representation. So if you get that representation, how to find small one is not obvious to me.
Okay, so since we're out of time, let's take all further questions offline. Let's thank the speaker again.
Thank you.